Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. We are in the 5th module of the course. The title of this module is Transport Phenomena of Non-Newtonian Fluids Part 2. So, this is the third lecture. In previous two lectures of this module, we have seen the flow of power law and Bingham plastic fluids between two infinite parallel plates, and then flow of LS model fluid and Bingham plastic fluids along inclined plates or vertical plates. That is what we have seen. So, in this third lecture we will be seeing the power law fluids flow in concentric annulus. Let us have a look at the geometry first. So, we have a kind of cylinder here or circular pipe. Okay. So, like that shaded portion here. The radius of this inner pipe or tube is sigma r, right. So, there is another cylinder here of radius capital R. So, whatever this annular space in between is there, this annular space, in this annular space the flow is taking place, right. So, if coordinate system, we can take the center of the inner pipe as a z axis, center axis of the inner pipe can be taken as z axis, and then this direction we can take the other direction, the radial direction we can take. This is the theta direction, but we are not worried about that one anyway now. Now, in general, if you see, before going to solve this problem in order to get the velocity profile and then volumetric flow rate expressions, physically we see here now the flow is not inside this pipe, but the outside of this pipe. So, then the flow is having some zero velocity or some because of the no slip velocity, zero velocity is there, and then the velocity increases to certain level, and then again because here the other wall also, let us say this location, the other wall also is having some kind of zero velocity. I mean, like because of the no slip velocity, both at the wall surfaces, both the walls, that is the inner pipe wall as well as the outer pipe wall, the velocities are 0. So, here tau wall some value will be there, and then here also tau wall some value tau, let us say tau wo is there. So, the maximum velocity where it occurs in between this annular space we do not know. So, if it is a pipe flow through a single pipe, then you can say that the maximum velocity is occurring at the center, but in this case you do not know which is the location where the velocity is maximum or which is the location where the shear stress is 0. Now, here this shear stress is having some maximum value, now it also decreases and then gradually it becomes certain location, at certain location it becomes 0 and again it increases. That means, if you see, now the let us say lambda r is the location at which the velocity is becoming maximum or the location of the zero shear stress point. So, let us say if this is the line, I am not saying, but let us say this is the line. So, then in this region from sigma r to lambda r, the velocity gradually increases and then it reaches to the maximum value at r is equals to lambda r, that is increasing the velocity gradient. Then from lambda r to the r, so again the shear stress increases and then the velocity decreases. So, then the velocity gradients decreases, that negative shear velocity gradient we can see. So, that means within the one annular region we have two kinds of flows, two kinds of flow regions. So, one is the region where the velocity gradient is increasing, that is between sigma r to lambda r, another region where the velocity gradient is decreasing, that is negative velocity gradient we can experience between lambda r to capital R. So, this makes the problem little difficult to solve analytically compared to the case of flow through single pipe. But however, we try to attempt and get the maximum information whatever possible by analytical solutions way. So, before going into the simplifying this problem mathematically, let us see the applications. In such geometry in general we find in oil well drilling, where drilling mud is circulated through annular space around drill pipe. Okay, and where in general these drill muds are obey Bingham plastic model or power law model or shear thinning behavior they in general show, or Bingham plastic viscoplastic behavior they show. Then we can also see such kind of applications in geometries like extrusions of plastic pipes and tubes. this geometry we can find in other applications like extrusion of plastic pipes and tubes. Then also we see such geometries in some kind of double pipe heat exchangers, etc. So, the length of the pipe, the concentric annulus is L. At one end the pressure is P, another end let us say P plus delta P. So, then the flow is taking place between because of this pressure gradient minus delta P by L. Okay. No, but we have to make a kind of list of simplifications or assumptions suitable to this flow problem, so that before going to solve this continuity and momentum equations, or before simplifying the continuity and momentum equations, which may provide some kind of information for us to obtain the velocity profiles. Okay. So, usually we do this kind of analytical solutions for the steady state flow, laminar and incompressible flow. So, these are the standard application for these kind of problems now. And then from this schematic we can see only Vz velocity is existing and it is function of r only, it is function of r. Vr velocity may be there, that may be very small compared to the Vz velocity, so that one can simply avoid it. We are not considering any gravity effect as well in this case. However, one can also include the gravity effect and then do the similar problem. Only difference that when we have the vertical annular region like this is the inner cylinder, then what this is the outer cylinder. So, whatever this sigma r and then this is r. So, this annular space, in the whatever the pressure terms are there, pressure term are added with the gravity terms and then define the modified hydrodynamic pressure. So, that the rest of the solution will have the similar form as in the case of laminar flow in a concentric annulus in the case of horizontal configuration. Now, let us start with the simplifying of the continuity equation. Continuity equation in cylindrical coordinates. So, the here geometry cylindrical geometry. So, these equations we should take in cylindrical coordinates. So, equation of continuity is in dou rho by dou t plus 1 by r dou by dou r rho r v r plus 1 by r dou by dou theta rho v theta plus dou by dou z rho v z is equals to 0, right. Steady state problem. So, first term is 0, there is no Vr velocity, there is no V theta velocity. So, second and third terms are also 0. So, we get dou by dou z of Vz is equals to 0 for incompressible fluids. So, what does it indicate? That flow is not changing in the flow direction, that is nothing but fully developed flow condition. That is nothing but fully developed flow condition. So, that means from continuity we get the information that the flow is fully developed. So, now r component of equation of motion we try to simplify. It is given here, rho into dou Vr by dou t plus Vr dou Vr by dou r plus V theta by r dou Vr by dou theta minus V theta square by r plus Vz dou Vr by dou z is equals to minus dou p by dou r plus 1 by r dou by dou r r tau r plus 1 by r dou tau theta r by dou theta minus tau theta theta by r plus dou by dou z of tau z r plus rho g r. So, this is the r component of equation of motion in cylindrical coordinates. So, now we apply the assumptions we have listed previously. So, steady state problem. So, this first term is 0, Vr is not existing, V theta is not existing. So, these terms are 0, Vz is existing, but dou Vr is not existing, as well as dou by dou z of any flow properties is 0 because of the fully developed conditions. Pressure we do not know anything. Tau rr is function of Vr only. So, Vr is not existing. So, this term is 0. Tau theta r is function of V theta and Vr, both of them are not existing. So, this term is also 0. As well, by symmetry also we can take off this term, and tau theta theta is a function of V theta only, which is not existing. So, this term is also 0, and then because of the fully developed flow condition, dou by dou z tau z r is also 0. R tau z r is function of Vz and Vr, right. Vz is function of r, r is so, and then r Vr is not existing, but Vz may be there, but however this term is 0 because of the fully developed flow, that is dou by dou z of anything is 0 because of this fully developed conditions, right. So, now another term is the gravity. In this geometry we have not taken any gravity terms. So dou P by dou R is equals to 0. That means we get the information that pressure is not function of R. Pressure is not function of R. Similarly, theta component of equation of motion is given here. This equation also, if we apply the assumptions, we have this steady state problem. So first term is 0, Vr is not existing, V theta is not existing, Vr, V theta both are not existing, Vz existing but V theta is not existing, as well as dou by dou z of any flow property is 0. So we cannot have this one. Pressure we do not know anything. Tau r theta is function of Vr and V theta, both of them are not there. So then this would be tau r theta is 0. So this term is 0. Tau theta theta is having only V theta term, so then which is not existing, so then this term is also 0. And then because of fully developed flow, this term is also 0. And these two terms are 0 for isometric for symmetric flow problems. And then there is no gravity term here as well. So what we get, dou P by only this term remaining, that is dou P by dou theta is equals to 0. That means pressure is not function of theta direction as well. So that is what we get. So now the z component of equation of motion is given here. Here also if we apply the assumptions, then see what we will get. So first term is 0 because it is steady state. Second term is 0 because Vr is not 0. Third term is 0 because V theta is not existing. Fourth term in the LHS also 0 because dou Vz by dou z is equal to 0 because of the fully developed flow that we got from the equation of continuity. Pressure we do not know, indeed pressure is existing in the z direction. Because of that pressure gradient in the z direction only, that flow is taking place. And then tau rz, it is having Vr velocity, Vz velocity, and then Vz velocity is function of R, so then we cannot cancel out this term. Vr is anyway not existing. So here V theta, Vz are there, but Vz is not function of theta, so it is 0. Fully developed flow, this is 0, and then there is no gravity in this geometry, so last term is also 0. So what we get? We get dou P by dou z is equals to 1 by R, dou by dou R, R tau rz. So this equation we may make use to get the required velocity profile, right? So until this point, if you remember, it is exactly same as in the case of flow through a single circular pipe, but after this point there will be some changes, right? So what we can see from this equation, that left hand side is function of z only, because before this equation we have already proven that the pressure is not function of r, and then it is not function of theta also, we have already proven. So it is function of z only. Okay, so left hand side is function of z only. Right hand side we have Vr and Vz. Vr is not existing anyway, Vz is there, and Vz is function of r here. So RHS is function of r only. So left hand side is function of z only, and right hand side is function of r only. So what we can do, we can treat them individually and then solve in order to get the required solution, because both of them are functions of different independent variables. So this equation, now first we take the LHS, that is dou P by dou z, let us say C1. Okay, so when you integrate, you get P is equals to C1z plus C2. Now the boundary condition, let us say z is equals to 0, P is equals to P0. Then when you apply this boundary condition here, you get C2 is equals to P0. And then other boundary in the lengthwise direction, that is z is equals to L, so P is equals to PL. Then you get C1 is equals to PL minus P0 by L by substituting here in this equation, and then taking C0 as C2 as P0, right? So when you substitute this C1 and C2 here in this equation again, we get the pressure distribution like this, which shows a linear dependence. The pressure distribution in the z direction is showing linear pressure distribution. So dou P by dou z is equals to C1, and then C1 is equals to PL minus P0 by L, that we can write at minus of P0 minus PL by L, that is minus delta P by L, that is minus delta P by L. So this equation, in equation number 3, dou P by dou z you can replace by minus delta P by L, and then solve this equation for RHS of that equation 3 to get the tau rz information. So now 1 by r dou by dou r of r tau r z is equals to C1 is equals to minus delta p by L. When you integrate it, minus r tau r z is equals to minus delta p by L r square, because before integrating you have to take this r to the other side and then integrate. So, r square by 2 plus constant C3, r tau r z is equals to minus delta p by L r by 2 plus C3 by r. Even this part also, up to this part also, it is exactly same as in the case of flow through pipes, flow through single pipe. Now, in that case, what we have in the case of single pipe, the flow through pipe, at the center shear stress is 0. So, in order to have a kind of r is equals to 0, if you substitute, it becomes infinity. So, in order to have finite shear stress distribution, we have taken C3 as 0 in the case of single pipe. Now, because of the double pipe, what happens? We have a two locations of wall shear stress, but there is no known location of the zero shear stress, right. So, then what boundary condition should we use here in order to have a kind of zero shear stress location? So, that is, once again, if you draw the geometry. So, this is what your inner cylinder radius sigma r, and then this is your outer cylinder radius capital R. So, here also let us say we have the shear stress tau W I, right, that is nothing but some tau R z at R is equals to sigma R, which is having some finite value, right, because at wall it cannot be 0, shear stress cannot be 0 if the flow is taking place. So, at this wall tau W O, let us say, so that is tau R z at R is equals to capital R. Right now, so they are, both of them are having some value. So, but we know that in between this annular space somewhere, that is between r is equals to sigma r, this is your r is equals to 0 line, between r is equals to sigma r, this is the line, to r is equals to capital R, there will be a location where the velocity would be maximum. Let us say this is that location. Let us say this is that location, that dotted line that I have drawn here, and then let us give this value lambda r, because we know this is a 0 velocity here. So, velocity increase and then to some maximum velocity, and then here again the upper wall again the velocity is 0. So, then from here it should decrease. So, let us say it is decreasing like this. So, this location, up to this location, as I already mentioned, the velocity gradient is positive up to this point, right, and then after that velocity gradient is again becoming the negative, right. So, this location of the maximum velocity, let us say r is equals to lambda r. We do not know what is that lambda, but let us say that location. So, at this location tau r z at r is equals to lambda r is equals to 0, because at this location V z is max. So, if you make use of that boundary condition at r is equals to lambda r, tau r z is equals to 0. So, then we have this expression. From here we get C3 as this expression given here. Now, you substitute this C3 back here, in this equation, and then simplify. So, then you get this expression as tau r z is equals to minus delta p by L r by 2 minus lambda square r square by 2 minus delta p by L 1 by r, because 1 by r is there. Now, what you do from here, minus delta p by L capital R by 2, if you take common, you will have r by r here minus lambda square capital R by small r, and then if you take small r by capital R as zeta, you can write this equation as tau r z is equals to minus delta p by L r by 2 zeta minus lambda square by zeta. So, this is the shear stress distribution. So, we can clearly see the shear stress distribution between annulus of two concentric cylindrical pipes is very different from the shear stress through one single cylindrical pipe. Okay. So, for two different geometries, the flow is, though the geometry is cylindrical geometry, but the shear stress is very different. So, obviously velocities also would be different. Okay. that is because here the flow is taking place in the annular region, not inside the pipe. Okay. Now, until this point we have not incorporated, until this equation 4 we have not incorporated the rheology of the fluid. So, now we incorporate rheology of the fluids. For power law fluids, we know the velocity gradient, that changes, and for power law fluids tau Rz is given by this equation. Tau Rz is equals to minus m into dVz by dr power n minus 1 multiplied by dVz by dr. So, this is the modulus here, right. What happens here in this case, the velocity as already discussed between r is equals to sigma r to r is equals to lambda r, it increases, and then after that towards the wall of the outer cylinder it decreases. That means at r is equals to lambda r, it changes its sign because of changing of the velocity gradient. The velocity gradient is positive in the lower region and then negative in the upper region. It is the same region, but the velocity is having two different distributions now within this annular region. So, we are just saying that Vzi in this region where the velocity gradient is positive, and then other region where the velocity gradient is negative, let us call the velocity profile Vzo. It is the same concentric annulus, same fluid, but the distribution of the fluid is having two different forms. So, then we are just separating by giving two different names. For two cases now we have to develop the velocity profile. So, velocity gradient is positive between r is equals to sigma r to lambda r, that is towards the inner wall region. Okay. So, where dVz by dr is positive, and then from lambda r to the capital R it is negative. So, either of the cases now we see. For the first case we see the case of lambda r is equals to sigma r to lambda r. In this region the velocity gradient is positive. So, we have this dVzi by dr, we take the positive. So, for power law fluids in this region we can say tau Rz is minus m modulus of dVzi by dr power n minus 1, dVzi by dr is equals to whatever the shear stress expression that we obtain, that is minus delta p by L r by 2 multiplied by zeta minus lambda square by zeta. So, since it is a positive, this dVzi by dr is positive in this region between sigma r to lambda r, it is positive. So, what we can say, this we can take this dVzi by dr power n, okay, so is equals to this is as it is in the right hand side. We can integrate this equation to get the respective Vzi if we know the location what is lambda, but we do not know what is that location. So, what we do, we write this equation and then keep it in integral format only and define a dummy variable x which is similar to zeta, So, x is the dummy integration variable. Okay. So, now then Vzi is equals to minus delta p by L r by 2 m whole power 1 by n integral of this thing. If you write in terms of the dummy variables, before integration what I am doing, this minus sign I can take to the other side. So, that it will be lambda square by zeta minus zeta, right. So, that is the reason it is written reverse here. Okay. Since this x is having dummy variables, that we have written because here it is in zeta terms, here it is dr term, and then we do not know the lambda. So, let us define a dummy variable x. So, that is having the similar form, r is equals to that is zeta is equals to small r by capital R, in that form only it is having. So, there is a additional r, here, right. This velocity profile is valid for this region, or which is same as this region. Okay. That is from the surface of inner cylinder to the maximum velocity location, which we do not know, right. We cannot integrate this equation because we do not know what is the location of lambda square, and also at the location of lambda r is equals to lambda r, velocity is changing its sign. The gradient started decreasing, that gradient started going into the negative direction, right. So, that is the reason we cannot solve this equation individually. We have to write the corresponding equation for the other region. So, for the other region, that is Vzo, that is between lambda r to capital R in this region, the velocity gradient is negative. So, whatever minus m modulus of dVZO by dr power n minus 1, this minus dVZO by dr. Now, the velocity gradient is negative. So, minus into minus plus we have written, and then dVZO by dr power n is equals to whatever the shear stress distribution that we got from equation 4 that we have already derived. So, here also do exactly the same thing. You take that m and then power 1 by power n to the other side, or multiply both side power 1 by m. So, then we have VZO is equals to minus delta p by L r by 2 m whole power 1 by n integral x minus lambda square by x whole power 1 by n dx. Here again the x is dummy variable of integration, okay, which is having the similar form as zeta. So, there is an extra r. Now, this equation also we cannot solve because we do not know the location of lambda, and then first one has to find out the location of lambda, then solve this equation 6 and 7 simultaneously. R at r is equals to lambda r, what we have Vzi is equals to Vzo is equals to Vz max. This condition has to be maintained. Okay. So, now from equation 6 what we have Vzi is given by this one, and then equation 7 Vzo, just now we have this one. In these two equations, this r and then minus delta p by L r by 2 m whole power 1 by n, here also minus delta p by L r by 2 m whole power 1 by n can be cancelled out, and then when you equate these two you get this equation number 8. Okay. So, whatever the velocity profile Vzo that we get, that velocity profile must obey this condition number 8. Then only we can say that velocity profile is correct. Now, the volumetric flow rate is nothing but q is equals to 2 pi integral sigma r Vz dr. R we can write it as in terms of zeta, that is small r by capital R is equals to zeta. So, small r is equals to r zeta. So, dr is equals to r d zeta. When you substitute these things, you have 2 pi r square integral zeta Vz d zeta, and zeta is varying between sigma to 1. But between sigma to 1 we have there is a lambda. So, sigma to lambda and then lambda to 1. In these two regions we have for zeta values of sigma to lambda and then lambda to 1, we have two different Vz values, that is Vzi and then Vzo respectively. So, those things we have to substitute here and then do the integration Okay. So, now whatever this equation 8, this equation and then this equation number 9, they must be solved simultaneously in order to have a reliable solution, and that is not possible analytically, because those two equations you have to simultaneously maintaining that Vzi is equals to Vzo boundary condition at r is equals to lambda r. So, that is very difficult to do analytically, but however that can also be possible if the cases of 1 by n are like in constant values like 1, 2, 3, 4 etc., then it can be done. Okay. So, indeed Frederick and Bird, they have evaluated this volumetric flow rate equation for constant values of 1 by n such as 1, 2, 3, 4 individually, and then for intermediate values of n they have done the interpolation and then provided a chart relating the non-dimensional flow rate, pressure drop and then power law index n. However, their results found that their accuracy of those results are deteriorating rapidly with decreasing power law index, that is increasing shear thinning behavior, or when the channel becoming more and more narrower. In either of the cases, the reliability of the Frederick and Bird solution deteriorating, the accuracy is deteriorating. So, however, Hanks and Larson also tried to obtain the volumetric flow rate, and then final expression is given here. What they have done, whatever this equation number 8 is there, that equation they have numerically solved it and then tabulated different lambda values for different n and then sigma values, corresponding lambda values they have given it tabulated, and then using those lambda values they have obtained the volumetric flow rate expression that is given like this equation number 10. So, Hanks and Larsen has provided expression for the volumetric flow rate for this case of power law fluid flow through concentric annular region, right. So, those values of lambda for different n and sigma values are given in a tabular form here, right. This table we can also find in the cross reference book by Chabra and Richardson, right. For different n values between 0.1 to 1 and then sigma values 0.1 to 0.9, they have given the table. We can see either n increasing or sigma increasing, these values are increasing, these values are increasing. Okay. So, now if let us say in place of the power law fluids, if we have the viscoplastic fluid, either Bingham plastic or Herschel-Bulkley fluids, the things will become more and more complicated, because for one single pipe flow itself, for velocity there are two profiles in the case of viscoplastic, that is the plug like region and then deforming fluid like region. So, here in the concentric region those things will become more and more complicated, but however a few people have done a kind of studies and then provided charts for different non-dimensional parameters. So, for those non-dimensional parameters, non-dimensional pressure drop, non-dimensional volumetric flow rate information they have given in terms of the chart. So, those charts, those details can be seen in this reference book by Chopra and Richardson. We are not going into those details. Now, however, before concluding this lecture, we will take a simple problem on Hanks and Larsen method, that how to get the volumetric flow rate, or if the volumetric flow rate is given, how to get the pressure drop for this kind of flow of a power law fluids through annular region. So, example problem, the statement is a polymer solution exhibits power law behavior with n is equals to 0.5 and m is equals to 3.2 Pascal second power 0.5. So, the question is estimate the pressure gradient required to maintain a steady flow of 0.3 meter cube per minute of the polymer solution through an annulus between a 10 mm and 20 mm diameter tubes. So, the radius and the size of the inner tube and then outer tube are given, and then flow rate is also given, as well as the rheological parameters of that fluid also is given, that is a power law behavior index and then power law consistency index are given. So, since R is given and then sigma R is also given, one can find the sigma R. So, R is 20 by 2, that is 10 mm. So, that is nothing but 0.01 meters. Sigma R, that is the radius of inner cylinder, inner tube is 10 by 2, that is 5 mm, that is nothing but 0.005 m. So, sigma is 0.005 meters divided by 0.01 meters is 0.5. So, sigma is 0.5 and then n value is also 0.5 and then n values are also 0.5. So, from the table given by Hanks and Larsen, we have to find out what is the corresponding value of lambda. So, when sigma is 0.5 and then n is 0.5, so lambda value is 0.7283. So, when you make use of this lambda value 0.7283 here, then you can solve this equation. So, the corresponding volumetric flow rate expression according to Hanks and Larsen solution is given here. So, in this equation everything is known except this minus delta P by L. So, when you substitute this n, r and then this small m values, lambda square, sigma values, etc., all these things if you substitute here and then do the simplification, you find this pressure gradient. The pressure gradient you get 169 kilopascal per meter. So, the information provided in this lecture are also adopted from this reference book Non-Newtonian Flow and Applied Rheology by Chabra and Richardson. Thank you.